Hello, this is Team 2, and this is our analysis and redesign of a vibrating bolt feeder. My name is Luke.
My name is Chloe.
My name's Ian.
My name's Kabir.
My name is Spencer.
My name is Gerardo.
So vibrating bolt feeder is primarily used in industrial manufacturing environments to automatically feed small parts into an assembly line. Loose parts are poured in the bolt and fed out in a specific orientation. We estimate our market size to be about $130 million with 100,000 units.
We have a primary and secondary set of customers. Our primary customer is the assembly division of manufacturing companies who require small parts for assembly, and a subset of that, or our secondary customer, is the staff that works on the line that makes use of said bolt feeder. This is the assembly CAD model of the vibrating bolt feeder that we analyzed today.
Shown here is the exploded CAD of our vibrating bolt feeder. The left side is the upper feeder assembly and the right side is the lower feeder assembly.
This is the product analysis. First, we have our FAST. It describes the functions our product will be doing. Then we have the assembly sequences. The one on the right will be the one we focus on when in design for assembly. These are the two comparison sequence tables, and then it shows the difference between them. This is a functional and component matrix. It shows all of our parts and the functions they will be completing. This is the bill of materials. This is a quad chart. We will be focusing on redesigning the one on red, but we also focus on the other parts to either get rid of them or redesign to make them lower cost.
This is the product family design. So the two functives that are different for each of our primary and secondary customer groups are the direct motion and secure assembly functives. Everything else is the same between them. So this means that if we look at the component commonality table, the part that becomes the modular part is the outfeed bracket, and the rest of them are the same between the two customer groups and are so part of the platform.
So in terms of the common interface for the primary and secondary customers, since the primary customer requires adjustability, we have an adjustable outfeed bracket, whereas the secondary customer has a non-adjustable version. Here's a picture of the adjustable outfeed bracket on the left and the static outfeed bracket on the right, and detailed CAD of the adjustable outfeed bracket. And then here's a product family assembly diagram showing the original and not optimized order on the top and the modified optimized version on the bottom, which is optimized for delayed differentiation.
And next I will talk about design for manual assembly. Shown here is the design for manual assembly time estimate table. And here's the second part. The time estimate before redesign is 1,274 seconds. The largest assembly times were for the least ring spacers, but looking at the quad chart and FCAMM, these are poor candidates for redesign. The largest remaining times were the bolt support spacers and outfeed bracket bolts. Shown here is a function component mapping matrix for manual assembly. It can be seen that the bolt support ring spacers and outfeed bracket nuts have very few functions, and therefore is another reason why we chose to redesign these parts. Highlighted in yellow is the outfeed bracket nuts and bolt support ring spacers. Again, these have low functional importance, and the bolt support ring spacers especially have a high cost, and so these were chosen for redesign. Shown on the right. The left image is the pre-redesign outfeed bracket, and the right is the post-redesign. We changed the mounting holes with through bolts to snap-on pins, and the picture at the bottom is shown the mounting holes on the alignment pin are threaded now to eliminate hard-to-reach bolts. For the bolt support ring structure, we eliminated 4 spacers and fasteners, and we merged the remaining spacers into the main part of the bolt. This reduces part count and also reduces fasteners. Shown here is the time estimate table for the post-redesign components. The final estimate was 1,169 seconds, and we reduced assembly time by 126.7 seconds.
This is the design for automated assembly. We took the large fixed base and the 3 small fixed base supports, and we wanted to redesign it to reduce all those base supports. By doing so, we reduced about 9 cents of assembly sequence cost. This is the before and after for modified base. So as you can see, we got rid of those base supports, and this is our function conformality matrix. The fixed base supports only did one function, so we removed them and we added that function to the fixed base. And then we removed that one part from our quad chart.
Okay, so next we're gonna talk about process selection. So this is the alignment pin that we redesigned for manual assembly. So a couple of key dimensions here, it's 75 millimeters long, 10 millimeters wide, 5.34 millimeters thick with two M6 tapped holes. Some key tolerance here are shown. The really important one is that the hole spacing is correct. So there's a tolerance of 0.1 millimeters because it has to fit with the mounting bracket. The length and the width are also important for directing parts, which is one of the functional requirements. So here we talk about the different processes that fit all of our different tolerances. So we ended up choosing machining because it can achieve all the required features and it beats electromachining and sheet metal forming due to the very large batch size of 100,000 and the threaded holes.
So here are the key dimensions for the modified fixed base. As you can see, it's around 430 millimeters in diameter and 115 millimeters in height. And the key tolerances are listed here. The tightest one is around 0.1 millimeters. So in terms of process selection for the modified fixed base, originally this was a cast part. We switched to injection molding, which requires some modification during DfM. Both injection molding and machining are capable of creating all the features. However, we decided to go with injection molding because it is cheaper and faster than machining, given the batch size of 100,000.
Next, we'll talk about the design for manufacturing changes. First, on the alignment pin, we ran it through DfM Pro, which didn't suggest any changes, but we knew we could do better. This is an overview of the changes with the modified part on the right. Specifically, the changes that we made was that we flattened the left end to allow for easier fixturing against a positive stop in a mill vise. We decreased the hole spacing to 15 millimeters, which is a standard round number, and we reduced the thickness of the part from 5.34 to 5 millimeters to eliminate the need for a facing process, as 5 millimeters is a standard stock size. According to Hubs, the cost of the part didn't change, but we did an analytical analysis and we saw that we saved about 5 cents per part with these changes, following these principles.
So for the fixed base, as Spencer mentioned, we switched to injection molding, which requires a pretty intense redesign. Before injection, we did this redesign, the cost per part was $291.96. So the features we decided to change after running this part through DfM Pro is adjusting the draft angle of the posts, removing excessive features to ensure uniform wall thickness, and then adding fillets to wire routing holes so there's no sharp edges. In addition, we reduced the wall thickness to a maximum of 7 millimeters to be able to produce this part using injection molding. As you can see here, there's a before and after of our DfM modifications for the fixed base. These callouts here mention exactly what was done. So you can see the draft angle was increased by 0.5 degrees. We removed unnecessary cutouts and bosses and reduced the wall thickness to a maximum of 7 millimeters. In addition, we added a fillet to the wire routing hole. You can see that there was a significant price decrease to $17.15 per part after the design for manufacturing changes.
All right, so design for product service system. So we decided to go with a leasing per hour of operation system. So basically customers lease the bowl for us per the hour they use it. And then the company handles all of the installation, servicing, and removal of the product. This allows for the product to have a longer lifetime because the company can guarantee that it is set up correctly and serviced correctly and at regular intervals. And it reduces the stress and responsibility of the customer to do all of this maintenance. In terms of DFE, the longer machine life from this improved servicing will reduce waste since the product will need replaced less often.
Next, I will conclude the presentation with the design critique and conclusion. For design critiques, we would recommend either adding a web or doing a vibration test to the fixed base because we reduced a lot of material in the modification for injection molding, and this would verify that the base does not form cracks. Another critique is that the alignment pin is only minimally adjustable, and another critique is that the snap fit reduces precision of the alignment pin compared to the through bolted holes. In conclusion, assuming roughly $35 an hour for assembly cost, we saved $1.21 per bowl feeder through design for manual assembly. We saved 9 cents per part through design for automated assembly, and through design for machining cost reductions, we saved $274.91 after redesigning the injection molding part, and we saved $0.051 per outfeed bracket, and there's 1 pin per feeder. Assuming the bowl feeders are automatically assembled, the total amount saved through DFA and DFM is $275.